60 years ago, this forgotten icon was the pinnacle of nuclear technology, a pioneer far ahead of its time, able to secure energy independence, provide cheap and reliable power for centuries without carbon emission, and greatly reduce dangerous nuclear waste. So why are we not using this technology today? The 1950s saw the most prolific advancement in peaceful nuclear technology. The United States experimented with different reactor design to supply a growing economy with reliable long-term electric power. One such promising innovation was the liquid metal fast breeder reactor. At the time, uranium was thought to be in short supply, and with its excellent fuel efficiency, low waste production, and long-term power reliability, the breeder reactor was the answer everyone was looking for. But this miracle technology comes at a higher construction cost and some safety challenges. After the success of the Clementine reactor in 1946, the EBR I was the first breeder to generate electricity. The moment was immortalized in this famous picture dated December 20th, 1951. The sodium reactor experiment in Santa Susana, California, and the EBR II reactor were experimental reactors able to generate some electrical power for the grid. However, none were designed for power production on the commercial scale. This next step was taken by a man named Walker Lee Czeisler. Walker was an engineer who helped rebuild Europe's electrical power generation after World War II and became the first president of the Atomic Industrial Forum. In 1951, as the new president of Detroit Edison, he saw the enormous potential of breeder reactors. Detroit was experiencing an economic boom, and the power demand was forecast to increase exponentially in the future of Southeast Michigan. In December 1951, Walker advocated for a nuclear power plant located in Michigan in his report submitted to the Atomic Energy Commission. The AEC approved the project on the eve of EBR I milestone achievement, which added more enthusiastic supporters to the project. After President Eisenhower allowed private company to own nuclear facility in August 1954, and after the tragic passing of Enrico Fermi in November of that year, construction permit moved forward for the new Enrico Fermi nuclear generating station. Construction began on August 8, 1956 at the Laguna Beach, an area on the shore of Lake Erie in Monroe County, Michigan, about halfway between Detroit and Toledo, Ohio. The reactor vessel, manufactured by Combustion Engineering, traveled 1,600 miles from Chattanooga, Tennessee, on barges, on the river, and rail to arrive on site May 1, 1958. On December 1, 1960, the sodium was loaded into the primary system, but Fermi I waits another 6 months for the first fuel shipment to arrive June 9, 1961. In December 1962, a sodium fire in the number 2 steam generator delayed the startup, but criticality eventually happened on August 23, 1963, 7 years after construction begins. A series of administrative delays slowed down the power assumption, but the AEC approved Fermi I for 100 megawatt thermal on July 8, 1966. Following this permission, in August, Fermi I operates safely and continuously for 53 hours at 100 megawatt thermal, accumulating over 1 million kilowatt hours of electrical power. The reactor building at the Enrico Fermi Atomic Power Plant is the heart of the complex. The main building, constructed by Chicago Bridges and Iron Company, was tested to sustain an internal pressure of 32 psi. It hosted a 90-ton reactor vessel entirely made of stainless steel. Designed for 300 megawatt thermal, the loop-tap reactor vessel was surrounded by 3 heat exchangers and the sodium pumps.
This is a steam generator building. There were 3 steam generators, one in each of these holes, and then the steam went to the turbine building next door.
1 million pounds of steam left these generators every hours of operation at 600 psi and 755 Fahrenheit to power the turbine located in the turbine building. A 150 megawatt electric power turbine made by Alice Chalmer and built early fall 1957 was ready for operation late 1960.
Well, my name is Lynn Goodman. Starting in 1996, I was the manager of Fermi I, and my title per the tech specs was the Fermi I custodian, which meant I was responsible for the license. And they learned a lot of information about Fermi I. I mean, it was the biggest breeder reactor in the world at the time it started up. People from all around the country came and learned here. I'd say at least 20 years ago, we actually sold the whole turbine side, including the condenser. It was going to be the power supply for a bauxite mine in Africa, but unfortunately the person that bought it electrocuted himself accidentally, and so we got it back. But it did get additional use at River Rouge. And it actually saved them a lot because the plant would have been down a lot longer if they hadn't been able to use our generator.
Fermi 1 had a 465 kilogram core made of 25.6% enriched uranium containing 10% by weight of molybdenum arranged in small square rods 2.5 inch wide, 12 rods by 12 rods with depleted uranium at each corner. 92 fuel elements formed the inner core with a diameter of 30.5 inch by 30.5 inch, roughly the size of a coffee table. This setup was surrounded by 2 fertile blankets of depleted uranium containing 3% molybdenum for ILO stability, durability, and strength. This blanket could generate 106 kilograms of fissile plutonium per year. The neutron energy spectrum in liquid metal breeder reactor looks like this. The dips are due to the sodium neutron scattering cross-section, especially around 5 and 80 keV. Most neutrons have an average energy around 1 MeV, which is 5 orders of magnitude higher than light water reactors. Instead of capturing a thermal neutron, most actinide can fission with the higher energy available. A breeder reactor can burn them, effectively reducing the quantity of long-lived nuclear waste. For example, in this area of neutron energy, the uranium-238 neutron capture is predominant, leading to plutonium-239. This occurrence drops above 20 keV and rises again as a double neutron capture between 7 and 8 MeV. This energy level favored the production of neptunium-237, and although long-lived, neptunium-237 is fissile above 1 MeV and can therefore be burned in the breeder. Some of the depleted uranium will fission especially closer to the core. Most of it will capture a neutron and decay to neptunium-239 in less than a half hour. Too short to statistically allow another neutron capture. This isotope can also fission under fast neutron, but will likely have enough time to decay to plutonium-239 in about 2.5 days, long enough before the next neutron capture. The most important region for neutron capture and plutonium-239 generation lies between 10 and 100 keV. Plutonium-239 is a fissile isotope. Over 80% of neutron capture will result in fission. In the rare event a plutonium-239 nuclei does not fission, a nucleus of plutonium-240 is formed, which can decay with a half-life between 100 nanoseconds and 6,500 years, depending on its energy level. Below about 1 MeV, the even number plutonium-240 is more likely to capture another neutron than fission, decaying into plutonium-241, which is fissile, thereby reducing its concentration. The same scenario repeats for potential higher actinide, less and less likely to be formed, and more likely to fission, releasing more fast neutron and energy in the process. The removal of long-lived actinides is important since the bulk of long-term radioactivity in used nuclear fuel remain dangerous because of the long-lived actinides like neptunium, americium, curium, and plutonium. We are left with a blanket of unreacted uranium-238, some fission products like cesium and strontium, very little neptunium-237, and a significant amount of plutonium-239 with traces of plutonium-240. Finally, very few, if any, higher actinides. As a side note, the concentration of plutonium-240 can be controlled during runs. This will be an important political factor for the future of Fermi 1. The blanket can be chemically or physically reprocessed to remove the fission product and neutron poison and reused as fuel in the breeder reactor. The ratio of fertile material like uranium-238 and generated fissile isotope is called a breeding ratio. Fermi 1 had a breeding ratio of 1.2, meaning it could generate 20% more fuel than it consumed. A non-moderating medium is needed for the fast breeder to work as intended. Water has an elastic response to fast neutron and slow them down below the threshold energy needed to fission higher actinides and for the production of plutonium fuel. Despite its chemical reactivity, liquid sodium is a perfect coolant. It does not slow down neutrons very much, and because sodium is a monoisotopic element, It mostly yields one radioisotope when exposed to high neutron flux in the core. Sodium-23 activates to sodium-24 with a low fast neutron capture cross-section and a short half-life. This does not happen often, and when it does not last long. Sodium-24 decays to magnesium-24, which is stable and soluble in liquid sodium. A neutron can also eject a proton from the sodium-23 nucleus, producing neon-22. This is a non-radioactive isotope and an inert gas that rapidly exits the core. Sodium is also cheap, plentiful, and has a very wide liquid temperature range from 98 degrees to 882 Celsius. As a metal, sodium heat transfer capacity is far superior than that of water, so less is needed. The vapor pressure of liquid sodium is also very low, so the reactor can be operated at or near atmospheric pressure. This greatly reduces the size and complexity of the vessel, pipes, pumps, and other systems, which can be scaled up with little restrictions. A sodium-cooled reactor can also operate at higher temperature than water reactors. This increases its thermal efficiency beyond 40% and allows for superheated steam virtually moisture-free to reach the turbine blades. Corrosion is also inexistent with pure liquid sodium. There is no corrosion product accumulation and no burst of rust. Sodium oxide is the main contaminant and is removed by the cold traps.
On the primary side, there was a cold trap that was in the sodium building in a room called the cold trap room. And there again, the primary sodium through into the sodium building, through the cold trap, and then back to the reactor building to purify the primary sodium.
Sodium as a coolant without fuel leakage can accumulate a significant activity. A water reactor coolant maintains an activity in the low microcurie per liters, while sodium can easily reach a few curies per liter. Liquid sodium is also not transparent. From the fuel and repair building, the fuel assembly travel on a cast car to and from the reactor building along this hallway to be introduced here. An ingenious system of carousel located within the inner reactor shield could hold a total of 11 sub-assembly. The offset handling mechanism transferred the new and used fuel to the core with a rotating shield plug, smoothly pivoting to the core position needed, all under liquid sodium. Fermi 1 did not chemically reprocess its fuel, but it was equipped to separate the blanket from the core by cutting the assembly for storage underwater and shipping. A 12-minute steam cleaning under inert gas allowed a transfer from sodium to water without violent reaction. The hold-down mechanism was designed to hold the fuel against the upward flow of sodium while in operation. This system had to be readjusted after some minor issue. Between the first criticality in August 1963 and March 1964, the reactor was taken to criticality 330 times and operated at low power for more than 1,000 hours. During that time, the Fermi 1 reactor exceeded expectations and performed extremely well. This led the AEC to issue a high-power license on December 17, 1965. Throughout, the mechanical, nuclear, and electrical component continue to perform in a highly satisfactory manner and exhibit no inherent instability or other undesirable characteristic. In February 1966, the reactor met all stability criteria for proceeding to higher level, and the output was raised to 67 megawatt thermal early April. In June 1966, the temperature gradient between incoming cooling sodium and outgoing flow between some fuel element was showing temperature discrepancy as bad as 47% higher. This returned to normal in July, and by then, Fermi 1 was licensed to operate at 100 megawatt thermal. The reading was high again in August, but far below the boiling point of sodium, and although concerning, a decision was made to rearrange the 4 fuel elements showing temperature differences and continue to run for further investigation. On October 5, 1966, under the supervision of licensed operator Henry Wilbert, some tests were scheduled to validate the main steam bypass, the off-gas fission product monitoring and sampling system, and the troublesome core temperature differences previously mentioned. At 2:20 p.m., the power was raised to 8 megawatt thermal, and the reactor was put on automatic control. The off-gas fission product monitoring device was fairly new, and instrument engineer Philip Herringham was in charge of keeping an eye on the reading for calibration. At 3:05 p.m., the feedwater flow control was put on automatic when Wilbur noticed the highly unusual 30 megawatt thermal power reading and checked the temperature chart recorder for the core sodium outflow. At the same time, between 2:58 and 3:01 p.m., Erringham measured about 500,000 counts for fission product in the off-gas monitor and no detector malfunction. That unusual reading sent him rushing for the control room. At 3:09 p.m., the radiation monitor alarmed for the reactor building ventilation exhaust system, and Wilbur immediately ordered the reactor shutdown just as Erringham entered the control room. Almost a year later, on September 11, 1967, the cause for the fuel overheating and clad rupture was found after complete drainage of the primary sodium. A media frenzy falsely reported a beer can caused the meltdown, and many speculated the cause of the incident, greatly exaggerating the situation. Sometimes before the first sodium loading in December 1960, someone noticed the bottom reactor intake had a conical shape. This geometry could allow enough of the molten core to gather in this area in case of a meltdown and potentially restart the chain reaction, making a bad situation worse. 6 plates of zirconium were installed to avoid pooling of the molten core in case of an accidental meltdown. 2 of the 6 zirconium plates, like this one, had become loose and one got stuck under the intake plenum. The zirconium plate restricted the flow of sodium to 2 of the 92 fuel subassembly. Overheating and deformation caused a minor fission product release detected and counteracted in time. This incident was the main driving force for a serious FME program. This program aimed to eliminate any intrusion of substance or object in sensitive system. Although not limited to the nuclear industry, every nuclear plant worldwide have a significant FME program since the Fermi I event. Straight path to the core engineering and potential obstructions, as well as late blueprint changes, were a big contribution from the Fermi I event of October 66. Despite the public outcry largely forgotten today, this incident was minor in scope and consequences. At the time before computer, there were no injuries and no contamination released outside the reactor building. The cause was identified and remediated. Everything worked as it should have, and the correct action were taken at the appropriate time. Almost 4 years after the incident, and with the approval of the AEC, Fermi I achieved criticality again on July 18, 1970. By October 16th, power level reached 200 megawatt thermal, and Fermi I logged over 8 million kilowatt hours by November 1970 and operated at full power for 10 days on December 1st, 1970. From 1970 to late 1971, Fermi I operated incident-free, performing 97 startups, 21 of which over 67 megawatt thermal, conducting research, training, and maintenance while producing over 32 million kilowatt hours for the grid. 262 personnel from 7 countries were trained on liquid metal reactor here in 1972. In 1970, President Nixon announced his energy vision for the future.
If you're going to have a clean and beautiful environment in this country, we have to have a new source of energy, plentiful and clean. And we can have that new source of energy. The place to get it, one of the major places to get it certainly, is through the development of nuclear energy. And that is that the United States was going to go forward in building a breeder reactor. Here we have the potentiality of a whole new breakthrough in the development of power for peace. That because private industry has already contributed $200 million to the development of the first plant, that I have decided to authorize going forward on a second.
At the time of the speech, Fermi I was approaching its license renewal deadline, and with the president's announcement of a government-funded second breeder at Clinch River, the power reactor development company who owned Fermi I was struggling to find more fuel for the refueling outage coming soon. Walker Lee Sizzler fought hard to finance the $50 million needed for the 6 years license using ceramic fuel. For 2 years, he reached out to public and private utility company, the United States government, as well as foreign entities to keep Fermi running. In January 1972, Walker contacted the AEC for license extension and continued operation. And on March 13th, he wrote directly to Nixon, and the president responded.
I have asked AEC Chairman Jim Schlesinger to review in depth the question of how the Fermi reactor can best aid the national program, and what role the federal government might play in addition to its existing commitment to the plant. Although a variety of technical and policy questions must be studied, I would hope that the AEC can complete their review in a relatively short time so that a decision can be reached as soon as possible. I have requested that Dr. Schlesinger contact you directly to make the necessary arrangement for this review.
Originally motivated and very supportive, the AEC executed a 180 early in 1972 and contacted Walker on March 29th with the following. We are unable to act upon the extension because of a need for further information to show adequate funds to sustain such operation. We request that such information be provided by April 30th, 1972. If adequate funds do not appear to be available, development of a plan for shutdown and decommissioning should begin promptly. Heavily modeled after Fermi 1, the new Clinch River project cost the taxpayer $2 billion and never generated anything. At the same time, Walker was looking for financial support. The fast flux test facility in Washington state cost $512 million. Similar to Fermi 1, the FFTF is an experimental research reactor. It has seen very little operation since 1993. Neither project generated a single watt of electricity. $6 million would have been enough to keep Fermi 1 running and online. Fermi 1 found itself on the wrong side of the March 5, 1970 Non-Proliferation Treaty, restricting civilian reactors from generating weapon-grade plutonium. Fermi 1 was fully capable of violating this agreement. Not every isotope of plutonium is usable for a weapon. Plutonium-240 has a small but non-negligible potential for spontaneous fission. This property makes it unusable for a fission weapon when mixed with plutonium-239 beyond about 7%. Because of the formation and accumulation of plutonium-240 in the core of a nuclear reactor, a short low-power cycle limits the production of the 240 isotope. Weapon grade was and still is generated in dedicated reactors. Commercial reactor breeders and light water alike do generate all the isotope of plutonium. This can theoretically be used in a weapon after chemical processing. In fact, the United States tested the theory in 1962 using reactor-grade plutonium containing about 20% of the 240 isotope. It was concluded that reactor-grade plutonium can in fact be used for a weaker weapon. A higher concentration of plutonium-240 can trigger the chain reaction before criticality, greatly reducing its explosive yield. The 5% increase in plutonium-240 for a tenfold decrease in yield is often cited, but is still somewhat debated and remains a sensitive subject. Because of its ability to run at low power for short cycle, Fermi 1 could and probably did generate weapon-grade plutonium. This put it at odds with the new law, and according to some, the Non-Proliferation Treaty was reason enough to shut it down. In August 1972, 21 reactor operators remained on site to assist with unloading the fuel from the core. Fermi 1 was operated at low power for the last time and shut down at 4:35 p.m. on September 22, 1972. The difficult decision to decommission the plant was taken the same year on November 27th. The Fermi 1 experiment cost was over 3 times the original estimate in 1966. To compensate for the intermittent power production, a border house was constructed to generate electricity when the reactor was down. Although no one was hurt and no radiation was released to the environment, the partial meltdown of October 1966 tarnished its legacy and reputation. Weapon testing and anti-nuclear sentiment of the late 60s and early 70s also contributed to this regrettable decision. Early 1973, the complex process of decommissioning was organized to remove the fuel, the sodium, and most of the heavy equipment. All 962 fuel elements from both radial and axial blanket were first shipped to Savannah River, reinforcing the suspicion of possible weapon-grade plutonium content. In 1974, they were moved to the Idaho National Lab here. Because of the sodium it still contains, the 34 tons of nuclear fuel required some innovative technique to deal with the hazard. As of 2025, the core of Fermi 1 is still being processed in Idaho. The non-radioactive sodium was shipped to West Virginia and handled by Fike Chemical, where a poor storage condition caused several explosions in 1976. All of the sodium was gone from the Fermi 1 site by 2012. The radioactive sodium was first stored in 55-gallon drums and removed in 1984. Built just before the incident in 1966, the Border House was the last addition to the Fermi 1 complex and the first to be demolished in 1999.
I've heard stories that they did operate at least once or twice with steam from both sides, but I don't know if that's true. I haven't seen it in writing.
Between 2008 and 2012, the neutron source, the reactor vessel, the offset mechanism, and the hold down arm were also removed, along with the heat exchangers. All areas of the plant are at background radiation level. The rotating shield plug still show very little radioactivity, and some minor contamination remain in the reactor building. Over its 10 years of operation, more than 1,000 delicate fuel transfer from sodium to water were performed at Fermi without a single incident. Fermi 1 was the first in many nuclear innovation. It solved countless engineering problems in the mechanical and chemical field. Multiple scientific challenges were also answered here. Along with operation processes, safety standards, and performance strategy, Fermi 1 cleared a way for future industrial-scale breeder reactors worldwide. Unfortunately, as a privately owned experimental reactor, it suffered from the financial burden of bureaucracy and political ambition. The 1966 incident was proof the worst-case scenario could be safely handled quickly and efficiently with no serious repercussion. Although the cause was very different, some similarity to the July 1959 SRE incident could have been a learning lesson long before the OE program. In hindsight, everyone's an expert. The future of Fermi 1 is in the hands of the NRC and the people dedicated to its safe decommission and conservation.
My name is Dan Sand. I've been at DTE for about 13 years as a project manager, and my current role right now is I am the senior project manager from PMO assigned to the Fermi 1 license termination project. Currently, Fermi 1 remains in safe store, so that's been the case since the 70s. The company has moved forward with decommissioning. We would say it's about 90% complete, and there just remains a very small amount of radiological contamination.
So that and the private ownership of the plant keep Fermi 1 off limit to the public.
Because we can't let people from the public just come and see this historical site, and it is eligible for listing as a historical place. Instead, we created the report and we have the exhibit at the community college.
If you are interested and wish to learn more about the story of Fermi 1, you can walk into the Monroe Community College, where the history of Fermi 1 is displayed. The visitor can view some historical artifacts, archives, and memorabilia.
We have a deadline from the NRC, 60 years after the plant terminates, that we're obligated to have the license terminated. That date for us is November 27th, 2032. Demoing everything is absolutely being talked about right now. My current direction for this project is only to terminate the license. It's not to demo everything.
Let's see. Unlike Fermi 1, breeder reactors may have a better future. A renewed interest in the technology have been floating around political circles. Resources challenges, accumulation of still useful waste, and climate change have pushed the US Senate and the House to sign the Advance Act of July 2024. This may allow the NRC to approve new reactor design, including the fast liquid metal breeder reactor. The use of sodium as coolant is a challenge understood and managed 70 years ago. Based on our current energy consumption, breeder reactors can run on waste nuclear fuel for hundreds, if not thousands of years. The TerraPower project in Wyoming is a promising new breeder reactor with a molten salt buffer for power management. The core of operation is essentially using technology pioneered by Fermi I. The Non-Proliferation Act of 1970 does not forbid breeders from operation. Rather, its aim is to limit the spread of fissile material usable in nuclear armament. Just like uranium can be used to breed plutonium, thorium can be used to breed uranium-233. This isotope can be weaponized as well. Similar to plutonium breeding, thorium generates uranium-232 in small amounts through double neutron capture. Unlike plutonium, this isotope is a strong gamma emitter, difficult to work with, and easily detectable. Although 30% of our nuclear energy comes from plutonium, light water reactors use uranium-235 as the main resource, which is less common than platinum in the Earth's crust. Using uranium-238 or thorium-232 makes sense when considering their abundance. Other countries have taken the lead in high power generation from breeders. China, Russia, and India have running breeder reactors in service. The largest to date was the French Super Phoenix, designed to generate over 1200 megawatt electric using waste from the 56 reactors in operation. It was forced into a shutdown and decommissioned in 1998 due to public misunderstanding, politics, and fear of the technology. That's why I think honest documentary and media like this are important to demystify the subject. As of 2025, no other source of power can meet our energy demand. Nuclear can address our needs with reliable, safe, cheap, and carbon-free electricity. And thanks to breeder reactors like Fermi I, we already know how to make it happen. If you want to learn more about Fermi I and its history, may I recommend the Fermi I New Age for Nuclear Power, where most of the historical data and information can be found. Constructive criticism is always welcome.